Okay, welcome everybody. Please do sign in and have a seat. Okay, so this is our department colloquium, the Electrical and Computer Engineering department. And we're doing something new this time around. We're actually also holding a seminar series for the Solid State Circuit Society, IEEE Solid State Circuit Society, and the Circuits and Systems Society. So we're combining them all together, so we'll have people from IEEE coming in, and also people from the UW community. And today we're going to start off this series, or this really an experiment in combining these two seminar formats with a talk on millimeter wave radar for automotive applications. But it's not just automotive applications. Sensing and radar is going to be huge in the future. And obviously solid state devices are going to play a big role in how successful those applications and how cheap they will be, small, et cetera. So they'll play a big role in these applications in the future. So I'm very honored to have a very distinguished speaker from Texas Instruments, came all the way up from Dallas. Brian Ginsburg received his BS, MS, and PhD degrees from the Massachusetts Institute of Technology. He then joined Texas Instruments in Dallas in 2007, working in its wireless terminal business unit. In TI's Kilby Labs, he developed a 160 gigahertz radar for proximity applications. In 2002, he became the system architect and RF design manager of TI's first generation 76 to 81 gigahertz CMOS single chip radar family. Now he is a distinguished member of technical staff and the systems manager of TI's radar team. He has served on the technical program committee for the International Solid State Circuit Symposium and is the program chair of the Symposium of VLSI Circuits, which is both the top-ranked conferences in the solid state circuits community. Now, before we get started, I just want to mention the students are signing in the back. I also have a sign-up form for people who are here for the IEEE talk. So I'm going to pass this around. We'll pass it around and have it go up to the back, and I'll pick it up in the back. And I'll have a pen with it. So with no further delay, I'd like to turn it over to Brian.
Thanks, Chris. Thanks, everybody, for coming. It's my pleasure here to talk about some of our work on millimeter wave sensors, and both for automotive and industrial applications. So just to begin with, take a picture of what a car looked like, a high-end car looked like in 2012, and what radars were available. So this is when the project started. If you were to buy, let's say, the top-of-the-line vehicle, you'd see anywhere between 3 and 5 radars around a car. These are for driving assistance functions. Most of them would be things like flashing a light for blind spot detection, or modulating your speed on a highway with adaptive cruise control. At the time, you had short-range sensors at 24 gigahertz, long-range sensors at 77 gigahertz. And each sensor had one specific function. So they were only trying to do one thing, and they were primarily only trying to focus on highway driving, which is the most controlled driving environment that we have. And this is just an example of what one of these radars looked like. So this is a slightly 2010 model, but it's hard to see here, but you can see this is the actual RF front end. So this is a 77 gigahertz front end. It is about 12 chips, all made out of gallium arsenide 3.5 technologies. Each one is a mixer or switch. And then the rest of the system is built around it. It had a etched metal waveguide plate that's not shown here as the antenna. And then all the other components were discrete and separate. Today, this is where we've jumped to, and I'll talk about some of the enabling technologies in this and what you can do with it. But essentially, everything that was on this entire top board is now fully integrated into one chip. And you can see that the antennas are just etched directly on the PCB, and this essentially reduces the form factor of the system and the weight and power dissipation of the system all by about 1 order of magnitude. And then finally, the next thing that we've been working on is how do you make this even smaller? Let's get rid of this component, the antennas. At 77 gigahertz, the actual wavelength is 4 millimeters. You can actually start to integrate antennas directly on the package that we provide with the IC anyway. And so this is sort of the next path, which is to have an antenna on package. I know it's a little bit hard to see on the screen maybe, but it's very hard to see on the screen. But there are 4 antenna elements for receivers and 3 antenna elements right here, all fitting on a 15 by 15 package. And now you can see this would be another essentially factor of 6 reduction in size compared to this. So with this, you're able to now have sensors with higher performance than they were 6, 7 years ago, and a much smaller form factor, and that allows you to place them in areas that you wouldn't otherwise be able to do and ideally enable new applications. So this is where the state of the art will be about next year on vehicles. You'll see a couple things. First of all the radar sensors have converged to 77 gigahertz. I'm gonna get into why that is. Some of it's driven by regulations, but most of this is driven by performance. You also see that the radar sensors, each of the radar sensors now essentially has 2 functions. For instance, the corner radar sensor, which used to just be looking at your blind spot on the highway, has a cross-traffic alert, and this is required for urban driving when you're going through intersections. And the forward-looking radar has a narrow beam for highway driving when you're on the Autobahn and trying to go at 160 kilometers an hour, and then a wide field of view for emergency autonomous braking, once again in urban environments. And then finally, there's a new Cocoon of short-range sensors around the car. These could be those little antenna-on-package versions. And these are used for automated parking and door opening applications. But with the same technology, automotive is just the tip of the iceberg here. So the same things that you can do with the automotive radar sensor, which is detect high precision position and distance, velocity, and angle, can also be used in many other applications. Some of them are very similar to cars, like robotics, where you're just trying to navigate the environment around a vehicle. And some of them are a little bit more distant, where that's a human interaction, where you can, let's say, maybe do a gesture recognition application. This is something that Google just announced in their Pixel 4 phone. Not our chip, unfortunately, but they have it. And then things, be able to remotely detect human vital signs, where you can the 100 micron or a few hundred micron movement of your chest wall as your heart beats and a couple millimeter movement as you breathe, you can detect in certain conditions with a radar sensor. So just one thing as I go forward on this, radar is obviously not the only sensor that's available. It's certainly not the only sensor that's in vehicles. There's a lot of sensing modalities. These are the ones that are most common in and around vehicles, and these are what are enabling ADAS applications today, which is driver assistance functions, where the driver's in control of the vehicle, but the radar might be telling the driver information they wouldn't have. And ultimately, the same sensing suite that would be used as the basis for highly automated driving, where the vehicle's in control of the situation and the driver would just have to be there in case a situation goes wrong. So the main ones would be video, radar, which will be the heart of this talk, LiDAR, which is the light equivalent of radar with active imaging, where you're using the same sensing modality, but at much higher frequency or shorter wavelength, and ultimately ultrasound. So in these, video is, of course, probably the most widely, the one that is most commonly used and sort of the closest to how we interact with our environments. We use our eyes. Video is the same set. And the one that's actually the largest total volume is actually ultrasound. These are those little holes in the bumper that you'll see on cars that are primarily used for very short range. Where radar really comes in is that radar is the sensing that has the longest possible range. So it's able to see, on highway driving, we regularly see over 200 to 300 meters, and is the most robust to environmental conditions. So won't go into much details on this, but if you have rain or fog, things where we know that the visibility degrades, that's why you can't see things in the optical domain, due to the fact that the particle size is actually smaller than a wavelength for the radar operation, you're still able to be pretty robust. So a radar can see and help steer the vehicle even under poor environmental conditions. The two places where radar does not do well, and is historically the reason why we still talk about video and LiDAR as essential technologies for highly automated driving, are first of all angular resolution. So the radar sensor the first radar sensor I'm going to show you has the angular resolution of a 12 pixel camera, which is, as you can imagine, terrible. So it's very difficult. Radar does very well at being able to separate objects in depth and separate objects in different, that are moving at different speeds. But if you have a static scene, which is sort of me picturing here, I would have 12 pixels to image this, the angle across here, and so that's very coarse. And the second thing is that partially because of this, because we have very limited angular resolution, classifying and understanding what's out there is more difficult. You can detect that something's there most of the time, but knowing is it a person or a Coke can, which actually have roughly the same size radar reflection, is very challenging. And of course, if you're driving, the car should respond very differently if it's a Coke can on the road versus a person. So we'll talk a little bit about that in the second half of the talk. So yeah, this is the main question, is how can you build a cost-effective, high angular resolution radar sensor that can classify objects and ultimately be either a complement or a replacement for, let's say, a LiDAR sensor, which is orders of magnitude more expensive. That being said, there's a lot of things in and around a vehicle that are driving a tremendous growth in electronics. And this is one of the fastest growing segments of electronics and certainly solid-state circuits over the last 5 to 10 years, and the projected growths are very high. Millimeter radar is one major component here of an active imaging sensor. But overall, in ADAS, those other sensor modalities I'm talking about, cameras, LiDAR, these are not going away. They were very complementary. Ultimately, the systems that can be able to take information from all those and fuse them in a way to have the best possible information about the scene, that's what's going to be required for us to give up control of our vehicles and let them navigate the environment. So I will actually jump in at this point and talk a little bit about the technology that we're doing. So some of this is a bit more of, how does a radar actually operate? What are we actually doing with a radar sensor? And so the radar modalities that we are using, which is pretty much where 99% of all vehicular radar is today, is something called frequency modulated continuous wave radar. So just as a background, the basic principle of radar is that you are sending out an electromagnetic wave. It goes out, it hits an object, and comes back, and you're just measuring the distance between those two. Now, the wave that you send out has dictates a lot of the performance of the radar system. And the waveform that we use is something called a frequency modulated wave. So this is actually the waveform that we send out. It is a sawtooth waveform in frequency domain. And so we have, let's say, a linearly increasing frequency over time. And then at the end, you just step back and repeat it one more time. This waveform goes out. It will bounce off an object and come back. And when it comes back, is actually, you'll see that it's shifted in two different ways. So the round trip time delay, this whole waveform is offset in time. So the received waveform will be a delayed version of the transmitted waveform. The second thing that happens is that you will see that the received waveform has a slight vertical shift. And this is due to the Doppler effect, which is that if an object is moving towards you, its frequency is actually a little bit higher. And if an object is moving away from you, its frequency is a little bit lower. For those of you familiar with astronomy, this is the blue shift or the red shift in astronomical terms. But this frequency difference is the so-called Doppler effect. And with the radar waveforms, radars that you can have, we can both measure the time delay and we can measure the Doppler directly. So range and velocity are sort of two unique dimensions for us, even though they are obviously coupled. So the way that the radar works is that if you can see here for this, you can see that there's a constant frequency difference between these two waveforms. So we use a mixer to actually multiply the transmit and the receive waveform, and we were able to extract this frequency difference. Now this frequency difference is proportional to, if you ignore Doppler for now, the frequency difference itself is proportional to range. So we look at the frequency difference of the two waveforms, and if you plot that in frequency domain, you will see that the closer targets will show up at lower frequencies. They'll have a smaller vertical gap here, and the farther away targets will show up at a higher frequency. The other thing that's sort of obvious on this is that the closer targets also are much larger amplitude. You'll get a much larger reflection typically from close-in objects. At the same time, if you actually look at the phase of let's say, this target, and you send out many of these chirps, so each one of these sawtooth ramps is called a chirp, you will see that the phase of this target will move very slightly from chirp to chirp. And that phase difference is because of the relative radial velocities of the radar and the target. And so if you can extract both the frequency difference and the phase shift over time, you're able to uniquely measure and separate out range and velocity. So those are the first two basic components of the radar waveform, the radar information that we get back. The third thing that radars can directly measure is the angle of arrival. So this is the angle towards the object. And this is, as I mentioned earlier, where we have sort of the coarsest ability to resolve signals. And the way that we do angle of arrival is relying on multiple antennas. And if you can see if an object, let's say the angle is coming in from the right side, the wavefront will hit the receiver over on the right side slightly before it'll hit RX3 and so forth. And this small time difference that you can have will be encoded actually as a phase difference. So if we can measure these time differences or the phase differences between the 4 receivers, we're able to estimate the angle of arrival. So with a single sensor, we'll get the distance and velocity, and with multiple antennas, we're also able to get the angle of arrival. And the key thing here, just to note, is that the angle of arrival that we're able to measure ends up being the precision of which we can measure this, or the ability to resolve multiple objects, increases as we have larger and larger numbers of antennas. So delta theta here, this is the, let's say, the angular resolution, the point at which we can separate 2 objects that are coming in at different angles, is simply inversely proportional to the number of receivers. So if you want to overcome the angular resolution challenge, you need to have a lot more receivers, and one of the differences between visible light and radar is that receivers are much more expensive for us than an individual pixel in an image sensor. Over time, the radar waveforms have moved to higher and higher frequencies. In automotive, as I was showing, at this point, everything's converged to 77 gigahertz. And the main reason that this has happened, well, one reason is there's been a change in regulations, but the reason they were asking for the change in regulations is because radar performance gets better at higher frequencies. And this really relates to the ability to separate out objects in space. So resolution is the ability to separate 2 objects in the radar context. And we can separate objects in any one of 3 dimensions. So the first one is range resolution. So if you have 2 objects and they're separated by a certain distance in depth, you can just separate them better with a wider bandwidth signal. And typically, more bandwidth is available at higher frequencies. Regulations allow for up to 5 gigahertz in the US at 76 to 81 gigahertz, which is obviously a lot higher than you would get at, let's say, a 2.4 gigahertz ISM radar. The second thing that we can separate out objects, and this is probably the one that's most difficult as a human to really get your mind about, is that we can separate out objects that have different radial velocities. So they can be at the same distance, they can be at the same angle, but we can uniquely determine that they're different objects if they have different radial velocities. And this is done, this improves as we go to smaller wavelengths, higher frequencies, as well as longer observation time. And the third one is the ability to separate out objects that are at different angles. This is related to the wavelength and the aperture size. And ultimately, radar is very good compared to other sensing modalities at range and velocity resolution, and particularly poor at angle space, just given the finite aperture sizes that we're able to use. But overall, as you go to higher and higher frequencies, all 3 of these improve. And that means we're able to get better spatial separation of objects. So just to dive in a little bit about what the architecture looks like to build this. So this is the chip I showed a few slides earlier that combined the entire 2010 radar sensor into one chip. At its heart, there is, over on the left side, or in the green box here, this is the analog side of it, the analog and RF. So we have a clock system that's generating these frequency modulated ramps. So this is a frequency ramp over time in that sawtooth fashion. I'll talk a little bit more about this as we go through the rest of the presentation. You have multiple transmitters. These transmitters include the ability to phase shift the beam. So you can do phase modulation. This is going to be used in some of the more advanced modulation schemes. Multiple transmitters and then multiple receivers, each with here, the mixer here, this is what will allow us to multiply the transmitted ramp and the received ramp. And what we get out is a constant frequency in the baseband that's proportional to range. Then finally, those are digitized, goes through a digital front end, and at the back, all the rest of the signal processing is done primarily in just a standard off-the-shelf DSP. And this allows you to do essentially the entire radar functionality of a corner radar all on one device. The one area that I'm going to focus on, because this is what is going to allow us to go into, be able to start to achieve higher angular resolutions and overcome that one major barrier for radar sensors, is the clock system. So this is just the example, very simplified block diagram of the clock system in our radar chip. At the heart, you have first a high frequency, let's say 14 gigahertz phase lock loop. So this is just like the heartbeat. It's a fixed clock that's just providing the timing for the overall system. It clocks things like the data converters, the digital on the chip. And then there's a 20 gigahertz frequency modulated continuous wave synthesizer. This gets the high frequency reference here and allows you to generate very precise linear ramps which are required to be able to send out to the scene. So at the heart, we have at 1/4 of the RF frequency, just a linear sawtooth waveform here. This ultimately gets multiplied by 4 and then distributed out to all the receivers and the transmitters. Now, I'm showing this here because when we go through and we talk about what does it take to extend beyond a single chip to multiple chips, this is going to be the key element. Before I get into what really is required to get into imaging and classification, which are going to be the major portion of the second half of the talk, I actually want to show what this looks like, and what are the types of things that we see when we're looking at radar images coming out of this chip. So this is an example. Certainly on the bottom right, you can see this is the normal view that all of us have with our eyes of what the scene looks like. And shown at the top right, this is the radar waveform plotted in Cartesian coordinates. So this is the same XY plot. There's no elevation information. We only have azimuth information here. But you can see as the car is moving around, it does actually, you can see the car outlined pretty well here. You can see it has many scattering points. And it sort of looks box-like. Maybe you can tell that's a car by looking at it. But certainly it obviously does not look like a camera image. Then on the bottom left, this is actually the radar waveform plotted in range Doppler coordinates. So this is the velocity, the radial velocity and the range dimension. And as you can see, as the car is moving around, you get these sharp lines, and as it turns, the sharp line sort of bends around. But it has a very structured range Doppler plot. Now, as Sandeep, the car driver, comes out, I want you to keep looking at the bottom left plot. As it comes into the bottom left plot, you can see as he's walking, this whole bottom left plot does not look like a car. It's sort of oscillating like this. So in range Doppler, he's moving around, and that's because when humans walk, unlike a vehicle, when we're walking, most of our body's going forward, but at the same time, our legs and arms are alternatively going forward and backwards. And this is one of the things that allows us to really distinguish different objects. And we'll talk about that as we get into classification. But that ability that non-rigid objects behave very differently in range Doppler domain is one of the key elements to get information out of a radar sensor. So the next thing I'm going to cover is really what do we do to get higher angular resolution and go beyond this sort of 12-pixel camera to something that is a little bit, starts to make images that look a little bit more realistic. So why do we want to get a higher number of channels? And this ultimately leads to, we want to be able to get more angular information, because when objects, especially the static environment has no Doppler information. Everything, if people are sitting still, in the Doppler dimension, everything has the exact same radial velocity. So we can't really get information and separate out objects that way. So we need to have a better angular resolution to be able to detect and image the static environment. This is true for both automotive environments, if you want to be driving and you want to be able to detect obstacles that might be sitting on the road, and also true in, let's say, a robotics environment where you're trying to navigate an indoor environment. And so if we can get multiple chips to operate coherently and all process the radar scene at the same time, now we can have a much larger number of antennas and be able to get more better imaging of the static environment. So the key thing here is that at the chip level, we have to be able to allow these things to tile and to be able to tile and still maintain synchronicity and coherence across the entire array. And so just taking a look here, remember this is the configuration where we're generating these modulated sawtooth waveforms right here at 20 gigahertz. So the first thing that we do is we allow for having multiple chips. We want all the chips to have a coherent clock. So this sawtooth waveform has to be exactly the same on all chips. It has to have the same timing, and ideally we want it to have the same noise. This gives us beneficial properties since the radar's transmitter and receiver, they share the same oscillator. There's a benefit, the phase noise that's present there, which is the intrinsic noise in a clock system, gets canceled in the receiver, and that significantly improves the signal-to-noise ratio and the dynamic range of a scene. So the master will have one of our devices be considered as a master. It will output its 20 gigahertz clock onto the board. This will get routed to all the slave devices, and then on the slave devices, the 20 gigahertz will come back, and then its synthesizer is turned off. So first step is to be able to share the synthesizer timing. or synthesize your waveform across all the devices. The second thing that's required is that the data converters, they also have to be sampling at the exact same time. If the data converters are sampling at different times, then we will get some range-dependent errors, because the objects that show up at further ranges, they will come up at a higher IF frequency, and timing mismatch there will then lead to objects at long range will be off to the side, an angle error based off of range. We want to avoid that. So the master's device also provides a synchronization signal that goes to all the slaves, and all the devices also share the same 40 megahertz time base. So this is what allows us to have a coherent radar system across multiple devices. And this is just what it looks like. This is a prototype that we've built up. So you have 4 sensors here. This one is the master device. Doesn't look that much different than the rest of them. But it is outputting 20 gigahertz signals. They get split on the board here and here. These are 2 Wilkinson dividers, for those of you familiar with microwave circuits. And then these signals gets fed back to the slaves, and also it feeds back to the master itself, so it does not have any delay compared to the slaves. And then from there, you can build up an antenna array. There's a total of, in this case, 16 receive antennas and 12 transmit antennas. And this allows us now to go from this 12 pixel imager to effectively up to 192 virtual channels for higher angular resolution. So just to show what this looks like, the basic operation mode is something called MIMO, or multiple input, multiple output radar. Many of you might be familiar with MIMO from communication systems. If you've been following some of the, let's say, more recent advances on 5G or more recent Wi-Fi, MIMO on radar operates a little bit differently, but it still uses the fact that all the transmitters and all the receivers can operate coherently. And the end result is that if you have multiple transmitters and you can separately measure the delay between all the transmitters to all the receivers, it is equivalent to having a virtual array of only receivers whose positions are the convolutions of the positions of the transmit antennas and the receive antennas. So if you can imagine here, we have 2 transmitters that are spaced at 2 lambda and 4 receivers that are spaced at lambda over 2, or half the wavelength. You get a virtual array with 8 antennas that are spaced at half the wavelength. And you can quickly see that as you have, let's say, an R system with 12 transmitters and 16 receivers, you can get 192 virtual antennas when they're all put together. And that allows you to get a much larger increase in the imaging capabilities for a relatively small increase in the complexity of the system. So what this looks like for us is that we have, in our case, we actually have in azimuth, so the horizontal dimension, we have allocated 86 virtual antennas. And then you can see that there's a number of virtual antennas that are separated out in elevation to be able to get coarse angular information vertically and relatively fine angular information horizontally. In our lab, we've done measurements in laboratory conditions to try to detect or measure the angular resolution of the system. So for the basic one with, let's say, 12 virtual antennas, this 3x4 chip, that has about 15 degrees of angular resolution. With this system, we have achieved 1.5 degrees of angular resolution. So now you can separate things out at, let's say, 100 to 120 meters that are separated by less than, about a meter. So how does this get processed? We get all the data that's coming in from the 4-chip Cascade board. So this is the baseband data for all 16 receivers. We do the range Doppler processing. So this is what does that 2-dimensional FFTs to separate out objects in range and velocity space. Then do detection to be able to detect what range velocity points we think there's an object. Ultimately, and then from there do direction of arrival calculations. Once we've compensated for the fact that in this large array with transmitters on at different times, there's a slight phase difference between each transmitter's virtual antennas. So that has to be compensated, and ultimately we're able to detect the direction of arrival of either points or as just a continuous distribution of a heat map. So this is just an example of what this looks like. So this is all static environment, which is the most challenging portion for radar. And first of all, from the camera side, obviously these still don't look like camera waveforms. And cameras, we're very used to seeing megapixel cameras. this is still only 192 pixels. So we're still talking about orders of magnitude smaller than a camera, but still an order of magnitude better than a single chip radar. And you can see in this is the TI parking lot down in Dallas. You'll have, we're now able to contour fences. You can see poles in the parking lot. You can see trees separated. Here we have two cars that are separated at 112 meters, which you really can't, even if we blew this plot up, you can sort of see the two cars here, but it's fairly long distance. You can see them cleanly. The other thing that's a much more challenging scenario, cars are very big. People are actually quite small. So the effective radar cross-section, or the amount of energy that comes back from a person, is somewhere between 10 and 20 times smaller than you get from a car. But you can still see that we have a person that can cleanly be distinguished between two cars at a few degrees angular resolution. And then as the vehicle's moving, you'll also be able to see things like the curb. You can see grass. So grass has a very different reflection from pavement. You can see that fairly clearly as we go around in the parking lot. The second thing that we want to be able to do, though, is to enable very long-range driving. So when you're driving around an urban environment, you want to be able to see everything, wide field of view. You want to know where people are and be able to do path planning. On the highway, though, people aren't coming from very, sort of wide angles. Highway driving is still very much very narrow, and radar is really driven by the German automotive industry, and that's all driven. All targeting Autobahn speeds, and they target up to about 160 kilometers an hour is the design target for these. And people do go faster, but already that's where all the system specifications are coming from. And that means we have to see 270 meters. So in this mode, rather than relying on MIMO, you can use transmit beamforming, where the transmitters themselves are choosing relative phase shifts so that they concentrate their beam in one particular direction. And that way you can get a much larger range. So there's actually a 10 log 10 increase, 10 log 10 number of transmitters increase between beamforming and MIMO modes, so you can see a much longer range. And this allows us to see well past 300 meters. Just as an example of what this looks like. So this is a video showing, and unfortunately I think it is not going to show up very well over here. You can see the MIMO mode will be limited to roughly 120 to 150 meters. And then with transmit beamforming, we can extend it up to about 300 meters. And I think I'll play this one more time. If you look at the dots sort of closer in as well, some of these, and I don't think it really shows up on the screen, so maybe that won't really help. But you can also see that the brightness of those dots really increases as the transmit beam sweeps across it, just because the signal to noise ratio is much higher in that narrow transmit beam, as you can combine both beamforming and MIMO modes. So the last thing that I'm just going to cover before opening this up for some questions is to take a look at what does it take to get beyond automotive. And this is, I think that there's a lot of opportunities to have new sensing modalities in factories, homes, buildings. And to do this, the radar sensors have to be it has to be relatively small and cheap. At the same time, the environments that they're going into are very different. So in driving, cars are very big, trucks are even bigger, things tend to be widely separated, and they're all moving. Inside buildings, for instance, things are much more cluttered. The total velocity distributions are much smaller. And we want to be able to still detect and interact with people, but at short distances, and this presents its own set of challenges. So to do this, we're going to be focusing on I'm going to talk about some of the higher level algorithms that can be running on these sensors to detect and separate out people in indoor environments where people are spaced closer than the angular resolution limits that the radar itself provides. And to get into this and how we were able to do that, basically be able to separate out people closer than the radar itself can do, we'll look here at the overall processing chain. So at the lowest level, the radar signals is generating just ADC waveforms that are proportional to it's a time domain waveform with multiple sinusoids. Each one is proportional to a different distance. That goes through low-level processing, which will separate out, it'll create a data cube of range, angle, and velocity in 3 dimensions, and you'll have a continuous distribution of objects in those 3 dimensions. Then there's a detection step. So this detection step will look at this continuous space, range, Doppler, and angle, and choose candidate points where the reflection is much larger than the surrounding noise environment. And that can be done right here at the low-level radar processing. Above that, now we have a bunch of points. And if you saw in the video earlier, a car could be maybe 30 points, a person might be 10 to 20 points. So you'll have multiple scattering centers, so you'll show up as many different points. And so the key here is the localization step is intended to take those points, combine those into objects, and then ultimately enable higher level information on those objects, ultimately up to classifying it and saying what that object is. And the key thing about the localization step that we have taken advantage of here, which I'll talk about with our group tracker, is that objects are real. These are real world objects. So individual points in the radar world will come and go. So if you're imaging a person from frame to frame, it's not like you always get 1 point for your head and maybe 1 point for your chest. You'll get points that'll sort of be slowly flickering around your body, and they're not very consistent. And this is because very small perturbations at the micron level can cause points to sort of constructively interfere and or constructively or destructively interfere with each other. So they tend to go in and out. But as a whole, you're still going to be getting lots of points. And objects, real people, they don't just disappear. Real people, they can't instantly jump from one portion of the scene to the other portion of the scene. They have state information. And it's that state information that allows us to be able to track and separate out people closer than the raw radar waveforms will allow you to do. So to show you, this is the group tracker. So this is based off of, this is what we do in this localization layer. So to begin with, let's assume you have two objects. So these are already things that we've identified as a real object. This could be a person, it could be a fan, outdoors it could be a car. So those objects themselves, they have a position, essentially a size, which is we model as a dispersion, and they have a velocity. So that's the state information that we have from them. And then we have a bunch of points that we've measured in this frame. So these objects will be tracked over a long time, many frames, seconds, minutes. And then every frame, which might be 50 milliseconds, will get a collection of points that we've just observed. So the group tracker is combining the step of clustering, which is separating out which of these points will belong to which object, and tracking, which is how these objects move over time. So the way that this works basically is that the first step is that based off of the known state information about the object's position and velocity, we'll predict where it is this frame. So we knew it was here last frame, and we knew it was moving along this vector. So now we think that the object is here. And as conveniently, this is in between the points that we've detected. But the separation between these objects might be below your actual angular resolution limit. So you can't cleanly distinguish all the points. It's not like these points are obviously one object and these points are obviously another object. If you just saw those points by themselves, it's not really sure which objects these belong to. So the second step that we have is the association function, which is that each object will predict which points around it might be candidate objects. And this is based off of knowing the historical state, how big this object was, and then using a gating function that's based both off of the position and the Doppler radial velocity of that object. And from there, those objects will essentially try to suck in points. So they'll grab the points that are closest to it and say, yes, these points are part of my object. Some points will be uniquely identified to a single object. Some points don't go with any historical object. And then some points you can see, obviously, there's a conflict because we're below the resolution limits, or the effective dispersion of the objects is larger than the spacing to this point. We need to have some sort of measure for assigning this, and this is just based off of likelihood function of saying, is it more likely to belong to the blue object or the green object? Finally, once all the points have been identified, we will update, or the innovation step is to update our estimate of the object's state. So estimate its position, its dispersion function, as well as its velocity. And then this process repeats. And by doing this, knowing that the objects themselves have some historical state, they can, over time, be able to retain object information, even if the objects themselves become too close to separate out by just looking at the raw points in that one frame. And just as a video, I'll skip that. So just to show what this looks like, so this is an example inside our lab, or inside our office, where we'll see on the top left will be the point clouds. So this will be the raw radar points. And on the top right are those bubbles that are the tracked object. And you can see as we're walking around in the lab, initially they might start out relatively far apart, but as they get closer and closer together, and you can see that the blue, if you can see here, the blue and the green dots are essentially are getting very close. Because of the ability to know the historic state, we're still able to cleanly maintain that there are 3 people the whole time. The other thing to note is that as Ming, the one in the black shirt, as she is going in front here, you essentially will almost completely lose the points from the object in the back. So the green, there's actually no points that become starved of objects for a couple frames. But once again, people, we have historical state information. We don't just instantly vanish and come back. So you can assume over time that if you have some knowledge of an object, you're able to maintain its state, and that allows you to get much better information out of a radar than you can by just looking at an instantaneous snapshot. So then the last thing I want to talk about is, okay, so it's interesting to see that we can localize these, but how do we detect what it is? As I mentioned before, on the automotive side, at far distances, a Coke can and a child have the same radar cross-section, about the same amount of reflected points and energy. But obviously, you want to be able to, don't worry about the Coke can. You don't want to hit a child. Indoors, it's the same thing. We want to be able to separate out people, which might be something that a security system would be interested in detecting, or an air conditioning system would be interested to know where people are, from other objects that are moving inside a home. And so this is what features can we look at to be able to separate these out. And the idea here is that we are taking the outputs of the point cloud in the localization step. So we now have objects which have a bunch of points associated with them. And then we're trying to look at the characteristics of those points to determine what it is. And the one that we're looking at here is just human, non-human. That was the main goal. And the non-human things that are in and around buildings that move, we've chosen basically 2 major categories. One is fans. So fans themselves, if you have a rotating fan, it has a lot of Doppler. So it shows up very brightly. There's a lot of moving components. And then also drapes. So drapes might be blowing by a fan. You don't want to miscategorize a drape as a person, and then suddenly you're sending a false alarm that is going to trigger your security system. So the features that we use, we can't rely on like normal, just looking at it and saying, oh, this looks like a person. You've seen some of these point clouds. They don't really look like people. So what we rely on are the microdoppler characteristics. So microdoppler is the distribution of velocity over time. And it's this distribution of velocity which appears very differently for different types of objects. As we saw in the vehicle, as the vehicle was moving, you got these very sharp ridges, very structured Doppler or range Doppler plots. And people, you had this sort of oscillatory, more free-form motion of the range Doppler plot. So in this particular case, this is a very simple example. On the point cloud on the right, we've separated out the points by the 3 different tracked objects. So there's 2 people, and there's going to be a fan that's located right here. And then in the microdoppler plots, which is essentially the velocity distribution, you'll see that they all have a wide velocity spread, but the fan is, once again, very structured. So the fan is just rotating at a constant velocity. It's going to have very discrete velocity points that you'll be capturing, and humans will be moving around over time. And we've trained a very simple classifier looking at these 3 microdoppler features. There's many more that people have proposed, and just I'll skip this for now, and just using that to classify the difference between a stationary fan, which is, you can see is the box fan here that's on, and then 2 people. And as you look at this image here, the red and the blue are this means that it's a human. So a color is human and gray is non-human. And this is just based off of a snapshot of the last 5 frames, the microdoppler signatures. And that, as they're moving back and forth, for the most, we set to see over 95% accuracy of the classification of a person and the fan. Occasionally, especially as the fan is getting closer, as the points between him and the fan are getting closer together, you'll see that the fan does flicker into a human. And not shown here, but sometimes if the human is standing still enough, the human itself might move back and forth. But this is just using a few different features and very short-term state information. Obviously, over time, if you look over the scene for many seconds or minutes, and you recognize that a person can't turn into a fan instantaneously and vice versa, you can get more higher level information to make these classification decisions. So with that, I just want to take the last couple minutes just to talk about some of the big challenges that are there over the next few years in the radar side. So I'm just going to talk about 3 of these. And this is the areas that we're actively looking at, our customers are looking at, and university research should also be taking a look at. The first is, I've talked about how to get higher angular resolution. We went from a 12 pixel camera to a 192 pixel camera. It's still pretty poor. And the biggest and the most challenging scenario, at least on the automotive side, is you have, let's say, a truck tire that's been blown out on the road. And your car is a level 4 autonomous vehicle, or even level 3, and it has to be able to decide whether it can safely go over this truck tire. And you have to make that decision at 80 plus meters in order to be able to safely either maneuver or stop on the brakes ahead of time. That truck tire is very close to the road. It's relatively low, and it's all static. So you're relying only on elevation angular resolution. So today, our sensor is about 1.4 degrees. With the same number of virtual antennas, if you just put them only in, let's say, only in elevation, you can get down to 0.6 degrees. You really want to get down to 0.2 or 0.1 degrees. And this is where LiDAR, this is why people are interested in LiDAR, because LiDAR itself, because of the wavelengths are so small, it can sort of have, there's no necessarily, the lower bound on resolution is very low. But they still want to be able to do the same thing with radar, both because radar is much cheaper than LiDAR, and we want to have multiple sensors that can detect objects. If you actually work out the math on this at 0.2 degrees, we're talking about meter plus of aperture size. You can imagine if you're driving a vehicle, it's hard to figure out how you'll get a meter of vertical height of a dense array. If they were willing to pay for it, there's not enough space on the front of a vehicle to be able to put that there. So this is not going to be, to get to these levels of resolutions, this is not just taking what I've shown here today and just increasing the number of chips. Obviously, we're TI, we want to sell a lot of chips. If you want to buy 80 of them and put them on the front of your vehicle, we're happy with that, but practically that's not going to be the solution. So this needs some other techniques to enhance signal processing, leveraging sparsity or leveraging motion to be able to really detect these extremely challenging conditions and ultimately be able to have fully autonomous vehicles. The second thing that's a big challenge that's coming up is sort of a nature of the success of radar. So radar as the number of radars around a vehicle has increased, the penetration of radar in automotive has increased a lot. At this point, most cars in the US, there's radar at least as an optional feature on them. And now when you have many radars in the environment, they're all sharing the same frequency spectrum. And unlike communication systems, where all the providers have gotten in a room and agreed on a standard about how to share the spectrum, the radar world, there's been no collaboration. Since each radar sensor by itself is a full-featured system, there's no sense of standardization in the radar world. And this means that the radar sensors have to be robust to interference from a wide class of sensors that may or may not be using similar waveforms than they are. And this will just be an increasing challenge in automotive. It's also a big challenge in, let's say, warehouses or factory automation, where you might have a lot of robots in a very dense space, all trying to navigate the environment safely and all sharing the same spectrum. In our case with FMCW, what you will get is when radars are radar waveforms, you'll see when they cross each other, you'll start to see these time domain impulses. These time domain impulses lead to a wide range in the noise floor after we go through the range Doppler processing, and that ultimately decreases the dynamic range of the system. So there needs to be techniques to be able to handle this, to mitigate it. Eventually, I hope we standardize this, but trying to get all these competitors to get in a room and standardize this, if you wait for that, it might be too late. And this is a safety system. They have to be able to work with many of these sensors in the same environment at the same time. And the last issue I'll talk about, which is partially solved today, but is only going to get worse, is what I'll call the bumper reflection. And this is in automotive, but it's present in all the systems. I didn't know this before I before I got into radar, but bumpers themselves are bumpers are relatively low loss plastic. So you can design a bumper to be essentially transparent for electromagnetic waves if you have the shape and the size, the depth appropriate. Then you have this nice plastic that's transparent and you cover it with paint. And the way you make different paint colors is you embed metallic nanoparticles in there, and that's how you get different paint colors. So for instance, bright silver paint has a lot of metal in it, and it has a dielectric constant of around 80. And then sort of like flat black paint will have a dielectric constant of around 2. And you want to make sure that your radar sensor is able to see through those equally. And you don't want to have a different radar sensor for every paint color. So people, they want to have one radar sensor that goes behind the bumper. They paint the bumper, it still has to operate. And so this is a major challenge for us, because when we go through this, most of the power will actually be reflected by the paint. So the radar waveform will hit the paint, it'll go through the bumper, it's just transparent, hit the paint, most of it will be reflected back. And since in an FMCW radar, the transmitter and the receiver operate simultaneously, we now have an extremely large jammer that's a very short distance. And this really severely limits the dynamic range of the system, and is a major challenge and leads to relatively high. We designed this by having relatively very low gain receivers with a fairly high, very high input preferred compression point, very good linearity, sacrificing a lot of noise performance to make this work. This is essentially a very similar problem to full duplex communications. And as there's been a lot of research there, we watch that very closely in order to see if there's techniques that can be adopted for that to improve the radar performance. So with that, just want to conclude, millimeter wave sensing itself provides high accuracy and resolution. It's critical for automotive. It's been Automotive Radar is the #1 millimeter wave market by far, much higher than communication systems. And the same techniques, the same principles that allow it to operate in cars have a lot of applications for in buildings, robotics, and other factory automation. But ultimately, some of the challenges are we need to go to much higher apertures or be able to achieve much higher angular resolution, and ultimately continue to develop a higher layer signal processing that can open up new applications, especially as we get into these indoor and more cluttered environments, which are not naturally as sparse in velocity. And so with that, I'd like to thank you for your attention.
All right, thank you for that excellent talk. I guess we'll open it up for questions right now. Yes, Janine.
Number one, talking about your tracking, looks like according to your terminology, it was the innovation prediction. Looks like it's a JPDA approach. It's a joint probabilistic data association approach using common filter.
It is common filter based,
right.
yes.
But this kind of approach has been widely used in 70 when we are talking about, for example, for airplane and all different kind of regular moving type of object.
Right.
But for human never really follow the common filter type of prediction and those kind of things. So do you think that can be extended to the normal human behavior next to your driving environment or next to your indoor environment, especially when we are talking about in a driving environment, we can see tens of people or even indoor, if you want to do people counting, we have so many people. Do you think that can be done easily?
So I think so certainly what we've found is that for very high densities of people, it breaks down. So you can't, if you're in an indoor environment, for instance, if you were trying to track people as they entered this room and we filled up this entire auditorium, our approaches completely break down. There needs to be new solutions that will come up. For relatively low numbers, 10 or fewer, and let's say a conference room, it works all of our experiments show that it's working fairly well, but we still expect that there's still gaps that can be improved. We have looked at some more computationally intensive ways of tracking and clustering, but they don't fit on our chips, like just the amount, particle swarms, for instance, are ways that we have taken a look at, which will go on to some of our higher end processors, but they don't work in the chips that we've had here. On the automotive side, we spent less time working on it. Automotive, obviously, common filtering is very standard for tracking cars. And in urban environments, we ourselves at TI, we haven't spent a lot of time looking at tracking in the automotive side. But for indoors at sort of low numbers, this works well. As we get to higher and higher numbers, this approach falls apart and something else has to come in. And that's something in between research or our customers. We expect that they can build on some of these techniques, but new ideas have to be added in.
Okay. Second question. For your classification part, you're still using those traditional human knowledge-based feature extraction before you send to the classifier. But at the same time, everybody knows now these days, we like to use deep learning and try to use those standard just input, then let the deep learning to decide what kind of feature, eventually what kind of classification result.
Right.
How come you didn't try that?
Actually, I'm gonna add a follow-up to that. That was my question, is what is the role of machine, I keep hearing classifier over and over again. What is the role of machine learning, I think is the question you're asking, in the future, right, for these type of sensing applications? Do you know, what kind of role will it play in the future?
So machine learning is going to be at the heart of a lot of this. This is a classifier that we're able to concoct pretty quickly. The major, when we get into deep learning, or which will basically combine the feature extraction and the classifier in one step, the biggest problem in radar versus vision is there's actually no good databases. So we're trying to, in the long run, we're trying to figure out, while this has been successful in other domains, is because there's a large amount, very large labeled data sets. Radar itself, I think there's no limitation to having deep learning applied to radar. It in fact would do very well. But the key is to how do you build up data sets that are large enough. So we've started to look at this and try to come up with more semi-automated ways of labeling data. I'm not showing that here because we haven't gotten that out yet. But that's our long-term, we want to be, and where our customers also want to be ecosystem-wise, is see, how can you create large enough data sets that you can meaningfully apply deep learning on it. And then the other thing is that when we're looking at this is, would it apply directly at sort of the raw radar data, or would it apply at the point cloud level? So in vehicles, what they're looking at is the low-level signal processing, which will go from the raw radar data up to detection, which is detected points, candidate points, of which there's many per object. That is right now still being considered to be done by the radar sensor itself. Then those detected points will be distributed through a medium speed network to a central processor that will fuse all those points and then ultimately do deep learning on the detected points. We're not showing that here. Our group, that's not what our group has been focusing on, but certainly that's what's already being done on the higher end vehicles today. The point that it actually goes away and you do that on the raw radar data, I don't know if that's going to happen anytime in the near future. Just the amount of the pre-processing that goes from the raw radar data to the detected points seems like that will probably still stay using classical techniques. But the deep learning on the point cloud is something that's already being done in like the central processor after fusion, which I'm not showing here, but that's sort of state of the art of where systems are.
All right, submit and then submit.
Yeah. So regarding your second problem about the multi-axis radar interference, so I realize you said that it's difficult to get radar vendors to standardize. But let's say cars will have radios, DSRC radios. Do you see a possibility that you can get radars to share spectrum, but via a radio side channel network?
Absolutely. I think that over time, they think that in radar vehicles are getting V2X and V2V communication. They should be able to start to split up the spectrum appropriately and dynamically based off the environments. So I think in the long run, this can be a solved problem. I don't think there's any technological barriers to making that happen. I think you're absolutely on the right track, is that we should already be leveraging the communication systems that we put into vehicles. The time frame, though, there's going to be a long time frame where, let's say, more sophisticated systems that might have been standardized will have to interact with these or survive these legacy systems. We're already at the point that there's something like 10 to 20 million, over the next few years, we're going to have 10 to 20 million of this class of radars that will be put into the roads, or 10 to 20 million vehicles per year that will be put into the roads over the next 4 to 5 years that will not be using, let's say, standardized approaches. So whatever system that comes up to replace this, it will have to be robust to the legacy systems that will be in the same spectrum. But in the long run, you're absolutely right. I think that's the direction that we should be going in. But it's unclear. As an industry, we move very slowly in terms of trying to go off and standardize it.
Two questions, physical layer. What's the approximate signal power?
So the transmit power?
Yeah.
So we're around 12 dBm per transmitter.
12 dBm.
So that's around 20 milliwatts.
That's fairly, what's the range, nominal range?
So it's very antenna dependent, but the Cascade system sees about 300 meters, sees a card of 300 meters. The single chip, if you put it with an antenna with, let's say, a 12 dBi antenna, you can see a motorcycle at about 120 meters.
One of the reasons I'm asking these questions is signal sharing, and what happens if you have a road full of these things that are all radiating this same kind of stuff, and they may or may not be interfering with each other, et cetera, et cetera. Are these licensed or unlicensed spectrum?
So it is essentially unlike, I mean, it is restricted spectrum, but it's not, there's no auctioning of the spectrum. So it's considered licensed, but it's not, individual providers don't own their own portion of the spectrum. It falls under Part 95. There's a reserve band for automotive vehicles, but it doesn't provide this. The spectrum, at least in the US, does not have any requirements on interference or anything else. But so one thing I will point out is that one thing that makes radar signal processing a little bit more robust, which is why we're able to still survive, is that there's a compression gain essentially from the RF bandwidth, which might be up to 5 gigahertz in the US, to the IF bandwidth, which is around 10 megahertz. And that means that compression gain naturally also suppresses interference. So you start off with a system that is around a 500x suppression of interference. So if you have small numbers of sensors or tens of sensors, you can sort of handle this. Once you get into hundreds of sensors, which you will see in a dense highway environment or a dense parking lot, then it becomes a big problem.
Okay, good. Maybe we'll take one more question from a student. Any students have a question? John.
So in the beamforming case for your multi-element array, I assume it takes a considerable amount of time to do the sweep across your entire angular range. Is there a latency issue when you're running at high speeds in beamforming mode?
So that's a great question. And there's some of the things I didn't talk about in terms of the SNR advantage. There would be a latency advantage. So normally beamforming would be if you have like a very small, you're on a highway, you only want to see maybe 5 or 10 degrees, and then you'd only sweep to a couple of points. And that way the latency would still be relatively small, that the objects would not be moving in and out of your beam. The thing that's actually more of a problem is that as you start to sweep your beam, and I didn't go through all the math here, as you observe each individual direction for a shorter amount of time, you lose a coherent processing gain from time dimension. So you actually, the SNR advantage by being able to concentrate the power is lost by the SNR disadvantage by not being able to integrate as long. So beamforming really only works well to improve SNR if you're only looking at only a couple different, 1 or 2 pointing directions. Once you get beyond that, the difference in SNR between beamforming and MIMO really starts to degrade, and then MIMO, which has better angular resolution, ends up being a much better system. So latency is not as big of a problem as the SNR loss if you have to sweep across many points. This video obviously does sweep across a lot of points just to illustrate what we can do, but this would be really restricted at, I want to see 150, 200 meters wide field of view, and then highway driving, plus minus 5 degrees, I know where I'm going. What's the furthest object out right there?
Okay, let's thank our speaker one more time.